Belinario. Ayun, nag-record. So again, good morning everyone. Welcome to Sir Belinario's BS Thesis Defense. The time is 10:31 and will be given how many minutes for the presentation?
30 minutes, I believe.
So 30 minutes presentation, then afterwards, for the remaining time will be questions. So you can begin.
Hello. All right. First, okay. Right. Hello. Mic test. First, okay po ba yung audio?
Yes, yes.
All right. Thank you. Thank you. Right. So, hello. Good morning, everyone. I am Carlo F. Belinario. This is my
Please record.
thesis.
Please turn. Yun.
Yes. Hello. All right. So,
Sorry, okay na pala. May recording na pala.
yes, ma'am. All right. So again, I am Carlo F. Belinario. This is my thesis entitled Gravitational Lensing Signatures in Gravitational Wave Signals from Compact Binary Coalescences. My thesis advisor is Dr. Reinabelle Reyes. We are from DNC of GANAP, Gravity, Astronomy, Nuclear, and Particle Physics Group of the NIT-UPD. First, I present to you the outline for today's discussion. First, we begin with the introduction, the motivation behind the selection of this topic, and then we will discuss the basics of gravitational lensing and our methodology, and then the results for strong lensing by the SIE and the enhanced microlensing, and finally, we summarize our work and give some recommendations for future work. So, for appreciation, we begin our discussion with a very, very brief history of gravitational waves. So gravitational waves, it has long been suspected since 1916 after Einstein developed his general relativity equations. So its linearization, as you can see here, these sets of equations, they basically tell us that the linearization of Einstein's field equations has a wave solution described by transverse disturbances of spatial strain traveling at the speed of light, originating from the time variations of the mass quadrupole moment of the source. And then like 100 years later, or 99 years to be more precise, we were finally able to detect the first gravitational wave signals, courtesy of the LIGO-Hanford and the LIGO-Livingston detector. So what they detected was a waveform that matches the predictions of general relativity for a coalescing black hole of masses 36 and 29 solar masses. And it has an excess of three solar masses radiated as gravitational waves. And sorry, and as of observation runs 1 to 3, spanning 5 years worth of gathering observational data from 2015 to 2020, we have at least 20 confirmed gravitational wave events. Now, the fourth observational run is scheduled on March 2023. It was postponed due to the global pandemic. And this time, we have 4 detectors in collaborating. We call this the LIGO-Virgo-Cagra collaboration, the LVK. And on March 2023, they will begin the 4th observation run. We also have here the LIGO India, which is the initiative for the building of a GW observatory in India. And then we also have this famous LISA, a space-based interferometer consisting of 3 spacecraft, and they are separated by millions of kilometers. And we expect that the frequencies of LISA will fill in the gap between the unresolvable frequencies on the ground-based observatories. Then, yeah, we also have this DESIGO. It's also a space-based interferometer, and it's based in Japan, proposed after the Kagra initiative. So, the growing numbers of detectors will allow us to detect more events and open new areas of gravitational wave research. And one of these is the notion of a gravitationally lensed gravitational waves. And yeah, so here, technically, the lensing of gravitational waves has not yet been detected. Okay. However, it does happen, and we expect that we will be able to detect this in the coming years because there will be more detectors. Now, basically, the lensing of gravitational waves follows the same principle in the gravitational lensing of light, where the presence of a massive object will cause the propagating wave to curve, or in this case, if a gravitational wave is traveling near the massive object, its trajectory will curve. And it will reach the observer at different paths, resulting in different images of the gravitational wave. And these images, they will be either demagnified or magnified, and they will arrive at different times to the observers. So, despite despite the gravitational waves not being detected, we still need to study it because, similar to light, the lensing of gravitational waves may offer insights on alternative tests of gravity. It can help us probe the lens structures. And in this case, for ground-based observatories, lensed gravitational waves may be used as basis both for possibly missed gravitational wave detections or for possible bias in the measured source parameters. And lastly, for the purpose of this thesis, we want to conduct this because we want to aid the future search for lensed signals. Now, we begin by discussing the basic concepts of gravitational lensing. Here in this figure, located on your left side, right? On your left side is the general configuration for a gravitational lensing system. So along an optical axis joining the observer and the center of the lens, you see that we can identify a source plane and a lens plane. The lens is located on the lens plane, and the following variables are as follows. So this ray of light will reach the lens at impact parameter xi, and it will be deflected by an angle alpha hat, reaching the observer at the curved path, as you see here. As a result, we see the source at the angular position theta instead of its true position at angular position beta. So this is the very foundation of gravitational lensing. And depending on the lens, we can have multiple number of images reaching the observer. Here, alpha is the reduced angle of deflection. Theta and beta are respectively your image and source position. The variables eta and xi are your impact parameters in the source plane and the lens plane. And the following distances here are your distances from the observer to lens, observer to source plane, and from the lens to source plane. Note that these distances are not your typical Euclidean distances. These are distances measured in angular diameter units. Now, from the Euclidean relation here, rather from this lensing geometry, we can obtain this Euclidean relation as described by equation 8.1. So this is valid because we expect that the angular positions are very, very small. So here we are in the small angle regime. And from equation 8.1, we can obtain the first form of the lens equation, which is simply given by beta equals theta minus alpha theta. Or we can re-express this in terms of the impact parameters eta and xi as follows in equation 8.3. Now, here we employ the thin lens approximations. Since most of the deflections occur at a distance perpendicular to the lens around delta z, and also since the distances between the observer and the lens between the source plane, we can approximate the lens to be a thin lens, just like in geometric optics, because we are dealing with great distances. In addition, the lens is technically a 3D mass distribution. However, we can project this on the lens plane by simply integrating the 3D mass distribution along the path where most deflections occur. This gives us the surface mass density sigma given by equation 9.1. And consequently, here, the deflection angle is given by the sum of all deflections due to the mass elements in the lens plane. And we have this integral to describe the angle of deflection. Now, we expect multiple images to arrive, and those images will arrive at the observer at different times, causing arrival time differences between the images. And in terms of the impact parameters, xi and eta, the arrival time differences is given by equation 10.1. We can reduce the dimension of this equation by employing the following substitution. So in terms of the dimensionless impact parameters x and y, we can select a length scale given by xi naught and eta naught given by ds over dl eta naught, and arrive at the dimensionless form of the time delay function given by equation 10.2. This is alternatively known as our Fermat potential, where psi x is the lensing potential in terms of the dimensionless impact parameter. And its relation to the reduced angle of deflection is given by equation 10.3. So equation 10.3 simply tells us that the reduced angle of deflection is simply the gradient of your lensing potential. Now, the reduced angle of deflection in integral terms is given by 11.1, where kappa x is your convergence and sigma sub CR is your critical density. Now, the Fermat potential has a differential form. By optimizing equation 10.2, we can obtain image positions xj for j number of solutions or images. And this process follows Fermat's principle, where the light will take the path that takes the least number of time to reach. So in this case, the differential form of our lens equation is given by the gradient of our Fermat potential. So optimizing the gradient of the Fermat potential will give us the image positions for j number of solutions. Now, here we transition to the lensed gravitational waves. The most basic equation describing a lensed gravitational waves is given by equation 10.3, wherein your lensed strain in the frequency domain is simply your unlensed strain multiplied by an amplification factor f of f. And here, f of f can be expressed again in terms of dimensionless variables as shown in equation 13.2. FW is just the sum of your magnifications times exponential of 2 pi phi j minus pi nj. And the next slide in the next slide we define the components of the previous equation. So here we have the image magnification given by 14.1, the Hessian matrix of in 14.2, and the Morse numbers, which are equal to either 0, 1/2, or 1 if the image are respectively the minimum, saddle, or the maximum of the Fermat potential. And then here we introduce the dimensionless frequency given by this equation, where Tm is our time scale given by this equation. So Rs being our spatial pages. And for dimensionless frequencies with values much greater than 1, the amplification factor here is dominated by geometric optics images, wherein those images will have different magnifications and time delays. Now, what do we expect to see in dense GW signals? Well, for point mass lenses rather, or PMLs, we will see the following beating patterns in the frequency domain of our signal. So here, you can see these beating patterns in the strain as the signature for lens gravitational waves. And again, for point mass lenses, if you try to observe the magnitude of your amplification factor, you would see spacings in the frequency. We call them the fringe spacing. And from the strain data in the frequency domain, we can identify these oscillations and select, say, for example, in one oscillation, we can select one maximum value and a minimum value in one oscillation. Using these features of the lens waveforms, we can estimate the mass of the point mass lens given by equation 15.1. So all we have to know is the fringe spacing in the amplification factor and get the ratio of the maximum and minimum values in one oscillation of the lens strain data. Now, we proceed with the methodologies in our thesis. So first, in this thesis, we use the lensing GW, which is a Python package for the lensing of gravitational waves. It has modules for a numerical calculation of image positions, and using the properties of those images, it generates unlensed and lensed gravitational wave signals. And in this case, our lens system of interest is given by this schematic diagram. We generate an unlensed signal from a binary black hole merger. and it will pass through this lens, where a point mass lens is embedded in a galaxy lens. And then we will try to analyze the resulting waveforms from this particular lens system. Now, for a higher level methodology, or the more abstract methodologies in this thesis, first, we performed validation tests for the image calculation of lensing GWs for the case of a strong lensing by the singular isothermal ellipsoid. And then we will compare the results with the previous analytic findings from a study we found by Asada et al. And next, we demonstrate the enhanced microlensing of the PML embedded on the SIE, and then analyze its resulting waveform. So first, we begin by the strong lensing of the SIE. First, we define what's a singular isothermal ellipsoid is. Okay, so SIE is derived from the SIS, the SIS, or the singular isothermal sphere. This model is used for spherically symmetric galaxies with stars which are behaving like an ideal gas in a hydrostatic equilibrium. And its mass surface density is given by equation 19.1, where sigma is your velocity dispersion along your line of sight, and xi here is our impact parameter in the lens plane. So in this case, Corman derived the equation for the SIE, which is just similar to the SIS, but this one is in terms of the minor axis of your elliptical lens. So here, instead of the impact parameter, the surface mass density is in terms of the minor axis given by equation 19.2. So equation 19.2 is our surface mass density, or rather the projected 2D mass of the SIE. Yeah, and yeah, Q here is the ratio of the minor and major axis of the ellipse. Now, Asada et al., they did some analytic works on the SIE, and they employed the following coordinate system. So for coordinates in the source plane, they are given by the coordinates beta 1, beta sub 1, and beta sub 2. And for the position of the images in the lens or image plane, they are given in terms of the coordinates theta 1 and theta 2. They were able to derive these coupled equations to solve for the image positions of an SIE, to solve for the image positions of the SIE constrained for the following eccentricities. So they constrained the eccentricity to less than 1/5, greater than 0. And in their particular work, they chose eccentricity equal to 0.15, which is within the constraint. Right, so for our lens configuration here, this is what they did. So you have your following source positions. One is at 0,0.1 here, represented by a circle. And then the filled disk for a source position, 0,0.5. And the square symbol here for source position at 0,1.3. Now, we try to calculate the images for the different galaxy masses, 10⁻⁷ to 10⁻⁻12 solar masses. We do this because this is the typical range for galaxy masses. And similarly to their analytic works, we also employ an eccentricity equals 0.15. And based on their findings, we should have the following images, or at least these are the sources, the source positions, or rather the image positions of the calculated images. So here, for example, for the image position at 0,0.1, we expect 4 images, 2 along the line of symmetry, the axis of symmetry, and another 2 images here in the third and fourth quadrant of this coordinate system. And then respectively for the 0,0.5 and 0,1.3 position, we expect these images. So here at 0.5, you should have 2 images along the symmetry axis. And for the square here at source position 0,1.3, 1 image only. So we use lensing GW to numerically find these images and arrive at the following results. So first, for the source position 0,0.1, we were able to recover 1 to 2 images, which are represented here by the red discs, out of the 4 expected images by Asada et al. So in this case, note that we are getting numerical solutions at the origin. However, we can discard them because their magnification is too low. Their magnification is around 0.001, so we can disregard them and consider the remaining images. And for this source position, 0.5, we were able to recover 2 images out of the 2 expected images. So for this particular source position, Lensing GW is able to recover all images. And lastly, here for the source position, 0.1.3, yes, Lensing GW is also able to recover the images, except for the case of this particular galaxy mass at 10⁻12 solar masses. So those are our first results. And next, okay, so next here we discuss our results for the enhanced microlensing. So first, let's just define what microlensing is. So microlensing is just lensing caused by the lens masses in this mass range. And here we define enhanced microlensing as the combined effects of your strong and micro lensing. So in this study, we employ the following lens configuration. We only selected one source position because this is where the Lensing GW has a valid results. And here we choose the SIE mass to be 10⁻6, which is just the lower range for galaxy masses. And then here we use a point mass lens of 100 solar masses and simulate an unlensed GW signal from a non-spinning binary black hole merger with masses 45 and 36 solar masses and inclination of 2.6. So here, so the enhanced microlensing, we considered two lens systems wherein we place a PML on top of the most magnified image, first at the positive parity side and the negative parity side of the SIE. We define these sides as follows. So for images on the positive parity, those are the images with Morse numbers equal to 0 or equal to 1, or alternatively, images which are the minimum of the map or the maximum of the time delay function. And consequently, the negative parity images are those whose Morse number is, this should be equal to n equals 1/2. And this is where the saddle, and these images here are the saddle points of the time delay. And yeah, so upon placing the point mass lenses here, we observe that the images are further lensed into multiple images. So say, for example, here on the positive parity side of the SIE, if we place a PML here on the most magnified image, this image is further lensed into 4 micro images. So let's define the conventions here. Macro images are just images resulting from the SIE only. And then the micro images are defined as the images resulting from the combined SIE and PML. So in these cases, we have the following micro images or the complete model for our lens systems. Now, we will try to analyze the resulting lens gravitational wave signals from these lens configurations. So in terms of, so in the frequency domain and the normalized stains, we observe the following. So first, our lens gravitational wave signals from the negative and positive parity lensing here, we see that they are above the advanced LIGO and the advanced Virgo detector, meaning that the lens signals are sensitive to both the detectors. And as you can see here, we take a look at our unlensed signal represented by this green line. Notice that it is above the LIGO threshold, but below the advanced Virgo detector, meaning that the frequencies consisting of the frequencies that consist your GW is only sensitive to the advanced LIGO and not to the advanced Virgo. However, we show here from our results that lens GW signals from enhanced microlensing will improve the strain amplitudes, making both lens signals detectable in the advanced LIGO and the advanced Virgo detectors. Of course, notably, we see the beating patterns once again in this enhanced microlensing setup. Now, we can calculate an effective mass corresponding to the PML mass that would generate the same beating patterns if we only consider the microlensing or the lensing of the point mass only. However, since we are employing the SIE as the strong lensing contributor, we will instead compute for an effective mass. So in this case here, we see that we can obtain the fringe spacing here in our amplification factor, and we can obtain this ratio from the beating patterns in the strain data. And doing so, we will arrive at this ratio, MF over M solar masses, equal to 7.83 times 10 raised to 4, which is effectively 3 orders of magnitude above our point mass lens. So this case, so in the case of lens signals from the positive parity side of the SIE, the effective mass of your point mass lens increases by 3 orders of magnitude. While for the negative parity side beating, for the negative parity side images, the effective mass you would get for your PML will increase by 2 orders of magnitude, as we can see here. So we just employed the findings from Bulashenko to have an effective mass, that should be a lower bound for the PML. However, we see that with the presence of SIE, the mass of the PML obtained from the lens gravitational wave signal will increase by 3 and 2 orders of magnitude for positive and negative parity GW lensing. So here we summarize our findings, and first on our validation test for lensing GWs, we found that yes, it identified the positions of the images, but it missed other images, especially for the case of, especially for the first case where we consider the source position at 0,01, 0,1 rather. We will report these bugs. Actually, we've reported these bugs to the authors for possible investigation. And then next, we demonstrated the effects of enhanced microlensing from point mass lenses embedded in SIE. And these results to the beating patterns in the lens GW signals and an enhancement of the strain amplitude in the frequency domain. And lastly, we quantify the enhanced microlensing effect of the galaxy by showing that your effective mass will increase when there is a point mass lens on the most magnified images, both for the positive and negative parity sides of the SIE. And then we also found that they are larger, or it increases your effective point mass lens by 3 to 2 orders of magnitude, respectively. And excuse me. Right. So recommendations for future works. We can actually expand this study and study enhanced microlensing of PML for other lens structures. So say we can investigate for ASIS, or even make a system of galaxy clusters. And yeah, we can also investigate lensing of GW near caustic sources, or along the lines where the magnification of the image is infinite. And yes, the lensing of GW, of course, can be used also to probe for dark matter halo properties. And yeah, that's it. And thank you very much for listening. This has been my presentation, and thank you.
Ayun, thank you for your presentation. Now let's move on to the question and answers. Maybe first my fellow panel member, gusto mo ba mauna?
Okay, sige. So thank you, Jean, for that very interesting and actually very interesting and very wonderful talk. So for my first question, sorry, baka hindi ko na siya hindi ko siya narinig kanina kasi lumabas ako ng konti. Can you again explain why PMLs are added sa analysis mo?
Right. Hello. All right. So we added PMLs on our analysis because we want to simulate the case where, for example, the SIE alone will produce. Wait. Let me just go to the slide. Part of this slide. This one. Yeah, this one. Schematic diagram. Slide 7. Ayan, this one. So we just want, we wanted or rather, its its equivalence in terms of physical observations is
Mm-mm.
sometimes there could be a point mass lens obstructing your image from the SIE alone. So remember that for our case, we should have two images for the SIE only. However, in the case that there is a point mass within that galaxy obstructing the one image,
Mm-mm.
the gravitational wave there will be further lensed into 4 images. And then
Okay.
and then yeah, so then we also do that for the other case. And
Okay.
Right.
Gets. So for can you parang tell me if it's observed in nature, ano yung representation ng PML sense sa isang galaxy?
yeah, so those PML, they could be your neutron, they could be neutron stars or just stars in general. Or it could also be a stellar mass black hole, but I believe the lensing by black holes is different. The physics of lensing by black holes is different. So in this case, the point mass lens, they represent the stars in general.
Okay, thank you. Much clear na
Thank
siya.
you.
Sige. Tatanong pa ba? May mga tanong din ako. Sige.
Sige, ubusin.
Okay. So another question is yung parang natural thing to ask is what other models are there? And based sa pinag-aralan mo ngayon, can you tell me when we use another lens model, what will be the expected results using this the lensing GW package that I
All right. All right. So we have different lens models kasi. So first here, we just use the SIE or the singular isothermal ellipsoid. Alternatively, we can also use the SIS here, this one, the CIS, as your primary lens. Or there's also an NFW model for dark matter, NFW model for dark matter. And this package actually has well, in the documentation of this package, there are many other lenses that you can use. You can even simulate just point mass lenses. For example, binary point mass lenses. Pwede rin siya. Or if you want a cluster of point mass lenses, you can position many point mass lenses along your search window, and then find the resulting images. So the reason why we use lensing GW is because sometimes your deflection potential is not analytic. So kailangan mag-trial and error ng values para ma-solve yung Fermat potential. So that's the primary reason for using lensing GW. And yeah, meaning you can employ a more complex system of lenses. So pwedeng combination ng SIS and SIEs and many more. So
okay. So actually tatanong ko nga din yun, what if maraming multiple lenses kasi maraming, di ba parang possible naman yun na nag-stack yung lensing na nangyayari.
Yes.
Okay, so that's good. Nasagot na din yung isa kong tanong.
Yay. Thank you.
Isa pa, so isa pa siguro bago magtanong sa iba. Bago yung iba naman magtanong. Ano lang, parang basic question lang. So, why do you think that this should happen? What makes you think na, sabi mo nga hindi pa siya observed sa ating mga observatories.
Right.
So what makes you think na this should happen and we should see this in our observations?
Right. So to answer that question, I think, well, we've also read different studies that predicts the observations of lens gravitational waves in the future. However, for now, from the available data, from the 20 confirmed events, there's no, how do I explain this? Yeah, there's no strong evidence yet for strong lensing. However, there were candidates for lens signals. If I may, okay, so we can just search it. Yung kila Broadhurst, yeah, they by Tom Broadhurst et al. They tried to study different signals or different GW events from the observational data in the O3 run and They found candidates. So they found three signals which could be images of a possible source. But I'm not really certain with how they arrived. Oh, I'm not certain with their statistical processes. But their conclusion was those three signals are candidates for strong lensing, but the probability of them being lensed is low. So with those analyses, there parang the probability is not necessarily zero, but but you can observe them. However, since we also discussed that there will be more detectors in the future, of course, we would expect to detect more GW signals, especially when LISA is in operation na. We should be able to detect more sensitive black holes, rather more sensitive GW signals, and further analyze whether those detections are images of possibly a single merger source.
Okay, so quick follow-up. So paano ulit? So maybe you have mentioned this, hindi ko lang nakakuha. So how will you again distinguish a regular gravitational wave signal from a lensed one?
Right. I think this is best. Okay, by this one, pakita ko muna yung sa this one, kila Bulashenko. Okay, so we distinguish lensed and unlensed gravitational wave signals as follows. So we take a look back here from the image by Bulashenko et al. So okay, of course, the unlensed signal should have no beating pattern. This is represented by the red broken line here. So in the frequency domain, dapat smooth siya ganito. Your unlensed signal should be smooth like that. And effectively, if you get the amplification factor of this signal, it should be equal to 1 lang because it's unlensed. But if it's lensed, the first indication that a signal is lensed is the occurrence of these beating patterns. So yeah, so this is one of their findings. There should be beating patterns for the lensed signals. So and then we also showed it here. This one, as you can see, if you take a closer look at the negative parity lensing, yeah, those are the signals look like they're oscillating, and we see here a more prominent oscillation here in the positive parity lensing.
Okay.
So, para siyang undulation again. And then we try
And
to
so
see the unlensed signal.
Yes, sorry. And question ko lang, in so far sa lahat ng gravitational wave detection data today, wala pang nakikitang gantong pattern.
Wala
Okay,
pa.
interesting. So is it just a matter of sensitivity or kulang lang talaga sa data, or sorry, baka ano lang.
I
Baka
think
nasabi mo
both.
na.
I think it's both. We need more data, and at the same time, we need more sensitive. We need to increase the sensitivity of our detectors.
Sige. Thank you for that. Sige, yung iba muna
you.
magtanong.
Ayan, thank you. Quick follow-up lang din doon. Bakit nagkakaroon ng beating patterns pag may lens?
Good question. Actually, let me just go back here. So bakit nagkakaroon ng beating patterns? Well, firstly, these are just the results by PML. They did the math here, and as far as I can remember, these oscillations are due to the interference ng images, because those images will arrive at the observer at different times. So mag-interfere. Dapat merong interference pattern yun, and the interference patterns are the beating patterns we see here.
I see. Anong ulit yung y-axis dito?
Okay. So for this case lang kila Bulashenko, nag-rescale lang kasi sila, but your y-axis here should be your frequencies. No. The y-axis here should be your the amplitude of your strain.
Parang amplitude. I see, for different frequencies.
And for different for different source positions. yung new nut dito is just the dimensionless frequency.
Mm-mm. I see. So yung beating patterns dahil sa interferences.
Interference ng
Okay.
images.
Um, okay, siguro ako na naman magtanong. Sir, okay. Sir, bye-bye. Siguro yung first question ko is, gravitational waves lang ba na affect nitong mga SIEs and PMLs? I'm thinking any object that passes through these mabebend talaga yung trajectory nila. Is that
Yes.
accurate?
Yes. Not only, so those lenses will not only affect gravitational waves, they will affect also all other electromagnetic waves. So yung light. Yeah, so light.
Mm-mm. I
Okay,
see.
pwede
Actually,
mag-jump in lang. Sige.
Sure.
Yeah, just to jump into the question lang din. Kasi question ko din siya sana, ano yung difference nito sa, kasi yung formalism, parang katulad siya ng EM na lensing eh.
Yeah.
Mm-mm.
So, can you tell us ano yung differences ng
Ano yung
EM
difference?
lensing
Yeah.
sa GW lensing?
All right. So their main difference is for EM lensing, of course, there is an optical signature. So for example, if there is a star sa likod ng lens mo, makakakita ka ng apat na image ng star, right? However, for gravitational waves, wala siyang optical signature kasi, well, we can see GWs with our naked eye. So we can only estimate their position, pero wala siyang like optical signature. So hindi natin makita yung light niya kasi hindi siya light. And yeah, so I think that's one of the main difference. Alam ko na ba itong isa. And I think yun lang yung difference niya. Yung difference niya with EM is lens gravitational waves, wala siyang optical signatures, hindi mo siya makikita with your naked eye, but yung lensing ng EM, you can see it with your naked eyes. And the rest follows from, well, actually kasi yung lensing ng gravitational waves, the formalism is just derived from the gravitational lensing of light. So, yeah.
Okay, so
Just a question on, and then follow up ko na rin. KG. Sorry, nasa same room kami. So baka nag-echo. Pero how about itong beating patterns? Does it happen for light? May analogous ba? Or is this special for gravitational waves?
So I think for this case, ma'am, this is special lang muna to gravitational waves dahil these interference patterns, may contribution dito yung amplification factor mo, and your amplification factor for now derived siya from the gravitational wave strain, which in principle is different from light kasi hindi naman strain yung metric mo for light. So for this case, I think these fitting patterns are unique lang for gravitational waves.
Yeah, pero interestingly din, parang may yung analog niya, it doesn't happen though for EM because of coherence. Parang hindi coherent yung light. Pero for GWs, you can see. Interesting.
Sige, thank you. Next question ko. Bale yung kinompare nyo yung results nyo dun sa analytic result for SIE.
Yes.
Bale automatic na that it also holds for SIS and PML since yung SIE lang yung chine-check niya. Tama ba?
Yes, especially for the PML because we have because for PML meron ng tests na nagawa with lens and GW and it matches the numerically determined image with different PML systems. So actually in the main paper, in the lens and GW paper, they tried it for binary point mass lenses and even for triple point mass lenses. And the analytic works are mainly done by Schneider, by Peter Schneider, you know him. And so far, it matches naman with the Lansing GW. For SIS, wala pa. Pero, just last December 2022, yeah, merong gumawa. And, yung sila, sila Tambalo and Zoom, ang hirap i-pronounce sa apelido, basta sila Miguel Zoom, for SIS. And we are following their work for now for possible expansion ng ginawa namin ngayon. So yeah, ideally, Lansing GW, yeah, you can try it to other lens sources, to other lens configurations, and even design your own lens system.
Okay. Tapos yung next question is, anong reason bakit nag-fail doon sa first case na doon sa position na 0.1 ba, tama?
Yes, sa 0.01. Yeah. Actually, to be honest, we are not sure why. However, we just take note here that when we performed this validation test, we just used the default setting. So the default settings include defining a resolution size for your search window. So for this case, resolution size namin is 10,000 pixels in a search window. So it's possible na dapat mas mataas yung gamitin na search window resolution para ma-obtain yung dalawang remaining image na to. However, for consistency, yung default lang muna yung ginawa namin para hopefully consistent din with other source positions. And just an FYI din, these codes, especially for the case of 0.01, runs 2 to 4 hours bago makuha yung image. So, yung 2 to 4 hours bago ma-determine yung red discs ito. So, for now, the only clue we have is it's possible that the images na hindi nakuha ng Lansing GW is due to resolution issues.
Pero what if may other cause ba? Resolution issue lang ba? Or
so far, yeah, that's the so far the resolution is what we suspect, because because it takes so long to run. We actually the 10 raised to 3 resolution takes like 2 to 4 hours to run. And we didn't really try to increase the resolution because we expect that it will run longer, so say for 8 hours. And yeah, we decided not to pursue it for now, and just have it reported muna to the authors. Yeah, so we reported it muna to the authors following our suspicion. Yeah, suspicion lang naman resolutions. But yeah, yun lang for now yung suspicion namin. Baka sa resolution lang siya, kaya hindi ma-obtain yung dalawang image.
I see. Sige. Thank you. Yan na muna from me. Let's maybe move to questions from the audience. Unahin ko na yung mga nag chat. Yung first is from Gabriel Dizon. Given our current detector specifications, what's the current smallest frequency binning that lets us identify the mass of TMLs?
Hello, okay. Okay, Gab, thank you for the question. Current smallest frequency binning that lets us identify. Gab, are you referring dito sa sa some kasi kung bins to, dapat it has something to do with sampling frequency? Hello, Gab? Ay, joke. So, problem ba to ng sampling frequency? Kasi, so, oo. Actually, I'm not sure kung ano yung smallest frequency binning. Pero I believe sa frequency kasi. Ang alam ko lang yung sa time domain yung millisecond ba yun? Millisecond yung time resolution. But for the frequency, I am not certain. Pero nga, pwede tayo tumingin ng ano.
Just go to the slide.
Yung ito.
You're asking about the effective mass, diba? Like,
Yes.
Ang question is, this is like
Mm-mm.
31 is the effective mass. Is that we can already do that with our current detector?
Ma ta- ah so meaning if mas finer yung frequency binning, teka lang, dapat mas resolute pa tong ano, kunwari yung FF. Okay, but for this case, what's the current small?
This case, this is already LIGO.
Yes, this is this is already LIGO, so yan yung.
So there's no problem.
Ayan, does it answer your question? Sorry, Gab is also here, so doon ako nakatingin. Okay. Alright, so thank you. Yeah, so okay. Yeah, so ayun. Thank you, Gab, for the question. I hope did it answer your question. Okay, thank you.
My second question pala siya sa chat na do gravitational lenses have a similar frequency response to optical lenses in the far field?
Gravitational lenses have similar frequency response to optical lenses in the far field. Alam ko far field na to kasi GO siya, geometric optics approximation na siya. And gets. By optical masses, you mean yung ano ba, yung parang optical lens lang na kunyari. Okay. So, in this case, yes, yes kasi part ng assumptions ng gravitational lensing is far field dapat yung gravitational lenses mo and analogous siya sa optical lenses na ginagawa like dito sa Earth. Ganun.
So there's a possibility that this can be reproduced in the lab.
Gravitational waves pero kasi
No. Optical analog.
Optical analog. I think yes. Yeah, I think yes. Okay. Ayan.
Sige, thank you. My question
Thank you.
Adrian, bye-bye.
Si Sir.
Hello, so question lang ulit, sorry. Pwede pabalik dun sa validation slides mo.
Validation slides.
Dun sa validation nung
This one.
Ayan. Baka di ko lang ulit narinig kanina kasi nag-CR ako. Ano ulit yung particular reasons why for certain, di ba yung una, tatlo yung analytical or apat ba, tapos sa pangalawa, dalawa lang. Sa last mo is isa lang yung analytic na finding. Ano yung may particular reason ba why is that or ano lang siya, parang arbitrary lang?
Okay, so yung solutions na to, this one, these image positions are the solutions of this coupled equation. So given your source position, okay, so if you have a source position, you have beta 1 and beta 2, and then the solutions of this coupled equation is the image positions here, or are the image positions here. And then, yeah, so for the case lang nung...
So ito yung three regime.
Yeah, three regime. Isang, by the way, these are the three regimes. Isa na nasa loob ng inner caustic. Yeah. One is inside the inner caustic. Oh, by the way, I forgot to label this one. But in the source plane, these lines, the lines you see here are the caustics, or the positions where the source will have infinite magnification. So in this case lang, ito yung three regimes. So this case is the regime inside your inner caustic. This one is the regime between your inner and outer caustic. And then 1.3 is for sources outside the caustics.
So itong source positions mo, general to dun sa formalism or source dependent siya? Kasi di ba particular yung pinili mo na source dito na non-spinning binary black holes.
Mm.
So what if nag-try ba kayo ng magbabago ba to if iba yung source mo, like let's say spinning na yung ano mo, black holes mo or something?
I think, wait. Okay, so pwede pa paulit ng tanong para mali ang pagkakagets.
So baka mali din yung pagkagets ko. So yung source positions ba na to is a general lang from the formalism or is it source dependent kasi 'di ba particular yung source na pinili mo dito sa ginawa mo, which is non-spinning binary black holes na nagme-merge. Tama ba?
I think for all cases na to, ma'am, no, kasi these are scaled in dimensionless units,
okay.
if you recall. So dimensionless siya. So
Kung light yan, it will still move.
Yeah.
And we will get the same image.
yes, we should.
So
Actually-
yung so go lang.
Sorry. Actually, this work by Asada is actually for the gravitational lensing of light.
Okay.
So for light din ito.
So
However,
sige, go lang.
So, however, ayun lang kasi they just use the images to predict. Well, they use the information on the images such as their magnifications, their time delays, to compute lang for the amplification factor sa lensed gravitational waves. So, the positions same lang sila with light, pero in terms of so sa position same lang sila ng light, same lang image position ng light and image position of the gravitation of the lensed gravitational waves. But for gravitational waves, may extra step because you need the properties of the images to solve for the amplification factor.
Okay. So yung follow-up question ko is, I don't know if you have tried it, but na-try mo na bang baguhin yung source mo? Like, maybe, or does it, what will happen sa results mo if nagbago sources mo? Like,
Right.
this time spinning na siya. Yeah.
So for this case, I think we should, I think our particular choice for, balikan ko lang.
Or pwede kahit yun na lang yung tanong, ano yung motivation why you chose non-spinning?
Exactly. So yung motivation dito is, we chose this one because this signal is just like what I've said, this is sub-threshold sa advanced Virgo and above threshold ng LIGO. We want,
okay.
so we chose this signal kasi we want to show how the enhanced microlensing can enhance the amplitude. So parang gusto lang namin maipakita na for signals between the sensitivity curves ng LIGO and Virgo can be enhanced para maging detectable sa dalawang detector.
Okay.
Yeah, so yun lang po yung motivation. But yes, in principle, we can also try for other gravitational wave signals. So it can be spinning.
May last final out there question ako baka kung okay lang. So what if neutron star merger siya, diba? Kasi diba yung 1817-18 na what if neutron star merger siya?
Star merger.
Like diba nung 1817-18 ba yan yung neutron star mergers?
Neutron star merging.
Diba meron siyang counterpart na optical na So dito ba sa study mo, can you siyempre, so expected din ba yung lensing doon or something? Baka walang sense yung tinatanong ko.
Okay lang, pero yes, gets ko. Yes, so for this case, po kasi di ba binary black hole merger. Yung I'm not sure if familiar kayo sa LAL, sa LIGO algorithm library. So meron kasi dong mga GW waveform approximants for black hole mergers and for black hole mergers. For binary black hole mergers, for binary neutron star mergers, and for neutron star black hole mergers. So iba-iba yung waveform approximants niya. So in this case, ang ginagamit naming waveform approximant IMR phenom V. So yun ata yung approximant for binary black hole. So if gusto natin ipakita yung sa neutron star, ibang waveform approximant yung gagamitin natin. And sa lensing GW, pwede mo siya palitan. Pwede mo ipalit yung wave approximant ng neutron star merger. And then, in principle, pwede rin natin gawin itong process na to for for the lensing of GW signal from neutron star mergers din.
Okay. So, cool lang interesting pala kasi talaga. Parang napaka-powerful pala talaga nung Python package na. Pero yun nga, I think marami nga na siyang work na kailangan kasi pinakita mo na marami din siyang mga bugs na possible na hindi ganun kaganda yung kanyang results. But yeah. So anyway, ano lang yun. Naisip ko lang. Pero thank you for that. Thank you for that.
Okay, so thank you everyone. It's already 11:31 a.m. Maybe kung wala nang mga quick questions dyan, we can end the session here. So ayun, thank you everyone. Any final comments
you.
from magpipicture ba ulit?
Good, sige, let's
Sige,
let's
can
give
picture.
Gina another round of applause.
Yay,
And
thank
then maybe
you.
we can do, if you want, a quick group photo with the audience as well to
Amo,
commemorate.
pwede ka na stop yung recording dito.
Okay.